Hello and welcome to the first lesson this week that's going to be revising radians. We're going to look at radian measure in general. We're going to be looking at areas of sectors. We're going to be looking at perimeters of sectors. We're also going to be using the sine and cosine rules. So this is a lot of revision of stuff you've done already but may not have seen in the same topic. So this is a quick recap of the sine and the cosine rules. So we've got triangle ABC. Our side AB is a length 15, side AC has a length 12, and we're given the angle BAC is 60 degrees. And we're asked to find some things about this. Now, it's always a good idea to draw a triangle if you're given a triangle question, just because then it makes it easier to decide which rule you need to use. Okay, so I'll just quickly draw this triangle in. So we've got triangle ABC, so see that's A, B, and that's C. AB has a length of 15 centimeters. AC has a length 12 centimeters, and angle BAC is 60 degrees. Find the length of the side BC. Right, so, the clue is in the title of the slide, really. We're going to be using the sine and cosine rules here. And this is just when we're using non-right angle triangles. The sine and the cosine rules are our friends in order to work out little bits of unknown information. So with this one, we're trying to find the third side of a triangle where we're given two sides and we're given the angle between them. Now, if we remember, first of all, our sine rule, and we've got sine A over A equals sine B over B equals sine C over C, where capital A, capital B, capital C are angles, and lowercase a, b, and c are the lengths of sides, and then we've got this relationship. Now we can also use the inverse of these fractions, so that a over sine A, b over sine B, c over sine C. It all just depends on what it is we're trying to work out. Essentially, if you're trying to work out the angle, put sine on the top. If you're trying to work out the side, put sine on the bottom. So what we're looking for when we use the sine rule is some matching pairs. We need to know the length of a side and the angle directly opposite it. Now, that's not going to work for this triangle at the moment, simply because we've got one angle and we don't know what the side is opposite it. Now, we could work out this side if we knew one of the other angles, because then we'd be able to use one of these fractions. So by elimination, because we don't have this matching pair of an angle and a side, we're going to use the cosine rule. Now, the cosine rule is this: a squared equals b squared plus c squared, a little bit like Pythagoras theorem. And then we take away minus 2bc cos a. Now, this is really important about the way the labels, the sides are labeled. Lowercase a is the side opposite this angle A, and that's massively important. You've got to get that the right way around. Now, as it turns out, this is exactly the rule that we're going to use. So if that's capital A, then that's little a. We can work out what little a is using the other two sides, b squared and c squared, i.e. these two, b and c, and cos of a, which is the angle between them. Now, you're not given the cosine rule in the formula book. You need to know it. So I suggest you learn it and you practice it during this lesson. So we're going to use the cosine rule. A squared, and the more you write it out, the less you're able to forget it. So b squared plus c squared minus 2bc cos a. And we're going to substitute in what we know. So we're trying to find a. B squared plus c squared, well, b and c are interchangeable, but we know that one of them is 15 and one of them is 12. It doesn't matter which one's which. So then 2 times 15 times 12 multiplied by cos of 60 degrees. Now, up to this point, obviously, this is going to be a lesson about radians, but we're working in degrees because our angle is given in degrees, so you just make that judgment. So then we can literally type into a calculator. So we've got 15 squared plus 12 squared minus 2 times 15 times 12 times cos 60. And we just double check that our calculator is in degrees, which mine wasn't. So there we go, it is now. And we get a squared equals 189. And we'll take the square root of that. We'll get our answer. So square root of answer, 3 root 21, or 13.7. So we'll write 13.7 centimeters. And we're done. Okay, so that's our length BC. Now we ignore the negative, obviously, because you can't have a negative length of a side. So next, we're asked to find the area of the triangle ABC. And when we're finding the area of a triangle, obviously you know that area is half base times height. But what you also know is that when you're not given information like the base or the height, and in this one, we're just not given the height, we could calculate it, which is essentially what we're going to do by using another formula, and there is this other formula. And the other formula is that the area equals half AB sine C. Now again, the ABC is almost kind of arbitrary here, but what we're saying is that it's 1/2 multiplied by one length of the side multiplied by another length of a side multiplied by the sine of the angle. Now the angle is in between the two sides. So from this triangle here, I've got 15 and I've got 12, and I've got the angle in between them. And that's what I'm going to work out. Now I know that this angle is technically called A in my triangle, but what I'm trying to get to is that's irrelevant. Okay, it's half times times the sine of the angle in between them. So we have half multiplied by 15 multiplied by 12 multiplied by sine 60, and then we literally just type it into a calculator and see what we get. So we've got 0.5 times 15 times 12 times sine 60, which is 45√3, which is 77.9 centimeters squared, rounded again to 3 sig figs. So that's our cosine rule mixed with area of a triangle. Now the only thing that we're going to add to this GCSE knowledge is that we're going to start working in radians. Okay, now I can't remember if my examples go straight into radians or not. We'll see. Not quite. So in triangle DEF, ED is for, and again, we're already kind of lost in the definition of the triangle here. So draw a quick sketch of the triangle just to help you. It doesn't matter what it looks like other than that it is a triangle. We've got DEF. So there's D, there's E, and there's F. ED is 5 centimeters. EF is 6 centimeters. And then we're told this information, sine of DEF, which is this angle here, sine of this angle is 2/3 and DEF is acute. Find the exact value of cos. Now, we have worked on questions like this previously. Whenever we're given the value of sine of an angle or cosine of an angle, and we're told some information about it being acute, obtuse, reflex, something like that, there's a standard method we're going to go to here, and it's that sine squared x plus cos squared x equals 1. Okay, now we're told that sine of DEF, now I'm going to call it sine x just for the sake of it, is 2/3. And I'm going to use that information in this identity. Okay, so always go to your sine squared plus cos squared identity when you're working on a question where you're given the information about acute or obtuse. So that means that we've got 2/3 squared, because that's sine of x squared. Sine of x is 2/3. Plus cos squared x is 1. So cos squared x is 1 minus 4/9, okay, which is 2/3 squared. And that means that cos squared x, if we do 1 minus 4/9, we get 5/9. And therefore, cos x is going to come out as plus or minus √5 over 3. Now, it's the plus or minus that makes us think then about the angle being acute. So we think about a sketch of the cosine graph. And we put in our key values of the cosine graph. We know that this is 90 degrees, this is 180, this is 270, and over here is 360. This is 0, that's 1, and this is minus 1. And we can see that where we have an acute angle, okay, i.e. between 0 and 90 on the x-axis here, between 0 and 90, cosine is always positive. The graph is always above the x-axis, all right? So for an acute angle that's cosine, the graph is above the x-axis, so it's positive, and so therefore cos x is √5 over 3, the positive one. So now we get into the question and we see why they wanted us to work that out. So we've got to find the length of DF. And that's it. Basically, it's a cosine rule question again. Because we've got two sides and the angle in between them. A squared equals b squared plus c squared minus 2bc cos a. That's the general cosine rule. So we're going to say that our length df squared is going to be given by the other two sides squared and added. So 5 squared plus 6 squared minus 2 times 5 times 6 multiplied by cos of the angle in between them, which is what we worked out in the first part of the question. So cos A is our root 5 over 3. And again, we'll just plug this into a calculator and we'll see what we come out with. So we've got 5 squared plus 6 squared minus 2 times 5 times 6 multiplied by root 5 over 3. It's a bit longer to do that root 5 over 3, doesn't it? There we go. So 61 minus 20 root 5, which is 16.3 to 3 sig figs. Okay, I've rounded that, but I'm going to keep the answer in my calculator. And then I'm just going to square root the answer to get 4.03 centimeters rounded to 3 significant figures. Okay, so it's a direct application of the cosine rule. This time we'd have worked out that cos A was root 5 over 3 from part A of the question. Then we're asked to find the angle EFD. So we're asked to find this angle in here. Okay, now I'm going to call it theta just for now. And we can see that theta is part of a matching pair. So it's directly opposite this 5 centimeters. What we also know now is that DF has a length of 4.03 centimeters, and that's directly opposite this angle, whereas this angle we know that sine is 2/3. So let's use all of that information together. We're trying to work out the angle. We're going to use the sine rule. So sine A over A equals sine B over B. That's all we need. That's a general way of writing it. But remember, these angles and these sides are opposite one another in the triangle. So if we look at, first of all, our sine x equals 2/3, right, from the initial question, that's what we're told about this angle, directly opposite 4.03. So we've got sine x over 4.03, so we've got 2/3 divided by 4.03 equals sine b, which is theta in my one. That's what I'm trying to work out as my angle theta. And the side opposite that angle is 5, so I've got sine theta over 5. And that means that sine theta is 5 times 2/3 divided by 4.03, and I'll leave that in my calculator. And then I'll do arc sine all at the same time. All right. So we're going to do arc sine, fraction button, 5 lots of another fraction button, 2/3. I've not typed in 5 for some reason, I've written 2, there we go, change it to 5. So 5 lots of 2/3 divided by our answer, close the bracket, and we get 55.7 degrees to 3 significant figures. Now we're not told that we had to work in degrees here. I'm working in degrees just because this is still a recap of our sine and cosine rules. So that one's a little bit more involved. You know, it's an A-level standard question on a GCSE topic. Okay. All right. Now feel free to pause the video, obviously, if you want to go back and review any of this. In the meantime, we'll go on and we'll start to use radians. So here we're going to start using radians. Now this is an A-level exam style question. You'll see a lot of these styles of questions, which basically have triangles with sectors of circles involved. So you can pause the video and take in the information, but effectively what we've got here is a PQR triangle. PQ is 10, here it is over here. QR is 14, here it is here. And QPR, this angle down here, is 0.7 radians. That's the only difference. We're not working in degrees anymore, we're working in radians. So good idea to switch your calculator to radians now, so that you don't forget when you're doing the bulk of the question. Find the size of that angle PRQ. Where is PRQ? It's over here. So we're interested in this angle over here, which I'm going to call theta. In radians to 2 decimal places. So all we're going to use for this one is our trusty sine rule. Now, the reason we're using the sine rule, let's go through that selection process. The angle we're interested in, we are given the side opposite. We have a matching pair. Do we have another matching pair in the triangle? Well, yes, we do. We have 14 centimeters, which is directly opposite the 0.7. You'll notice I'm ignoring this QS line and I'm ignoring a shaded area. So theta and 10 are opposite, 0.7 and 14 are opposite. So we use the sine rule where we're trying to find an angle. So we use sine A over A equals sine B over B. We only need those two aspects. And then we're just going to fill in the information from our question. So we'll say sine theta, the one we're trying to work out, divided by 10, okay, directly opposite, theta and the 10, is equal to sine B over B. So we've got sine of 0.7 radians divided by 14. Now, it doesn't matter that it's in radians. It actually doesn't affect the question in the slightest. All right, you just need to make sure your calculator is in radians and the working is the same. So that means that sine theta is 10 sine 0.7 divided by 14. And we can just therefore work out what theta is by doing arc sine of all of this in your calculator. Okay, so don't write down too many answers for this, just get straight to the answer that you need. So we're going to do shift sine, fraction button, 10 sine 0.7. Okay, doing nothing differently, just typing in 0.7 where my sine is, so, and then divided by 14. Close that bracket, and we get 0.478 to 3 sig figs. And that's in radians. 2 decimal places. So theta is 0.48. Done. So now we've got the point S lies on PR such that PS is 10 centimeters. The shaded region is bound by the straight lines QR and QS and the arc of QS, blah, 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 blah. You can see the shaded region, okay? So using a little bit of kind of compound area knowledge, how do you calculate that area? Well, if you knew the area of the whole triangle, and then you could subtract the area of just the sector, then you are absolutely laughing, okay? And that's what we're going to do. So first, we'll concentrate on the area of the triangle, and wherever we have a lack of information about the height, then we use half AB sine C. Which means that we need 2 sides, A and B, and we need the angle in between them, C. So from this question, we don't know how long this side S is. We're not given that information, but we do know that this is 10 from P to Q, and we know QR is 14. So if we can work out the angle in between those, then we're going to be happy days. Okay, so I'm going to call that angle X. Now, what we do know about angles in a triangle is that they add up to 180 degrees, but we're working in radians. So we have to then say, actually, they add up to pi radians. So we're going to use this fact, okay? We're going to use the fact that 0.7, as given in the question, plus my 0.48, as calculated in part A, which is this angle down here, okay? So 0.7 plus 0.48, plus X is equal to pi, because pi radians is the equivalent of 180 degrees. And so therefore X is just going to be pi minus those 2 numbers. So let's work that out. And again, we're not doing anything different here. We're literally just using pi in our calculator, the pi number. So pi minus 0.7 minus 0.48 comes out as 1.96 to 3 sig figs. And that's our angle at X. And so now that we've got that angle, we can then just apply this area formula. So we've got a half multiplied by, and I've forgotten my 2 sides, 10 and 14. So a half times 10 times 14 times sine of 1.96, and I'll leave that unrounded in my calculator. So then we've got 1/2 of 10 times 14 times sine of my answer, which is 64.7 centimeters squared to 3 sig figs. But again, I'll use that unrounded. So that's the area of the whole triangle. Now, the area of a sector. We have worked on this before. When we were using radians, we have studied this. We just did one lesson though, so I'm just going to remind you how it works. For the area of a sector, we have a formula. And the area of a sector, when we're working in radians, only when we're working in radians, is 1/2 r squared theta, where r is the radius of the circle and theta is the angle at the center between the two radii. And this theta has to be in radians. So let's put in what we know. So that is 1/2 multiplied by the radius. Okay, so we're looking at simply this sector of the circle now. All right, that's our sector. The radius of this sector is this 10 centimeters, okay, because it's part of a circle. P would be the center of that circle. This would be the radius, and PS, which we're also told is 10 here, is also the radius of this circle, but we're only dealing with the section. So the radius is 10. So we've got 1/2 times 10 squared multiplied by theta, and it is literally just theta, which is this 0.7. 0.7. So then I'm going to multiply by 0.7 without sign, without anything like that. So it's just 1/2 times 10 squared times 0.7. So let's do that, which is 35. Okay, so what did we say about the area that was shaded in? So we'll do the triangle minus the sector, and that will give us our answer. So we've got our 64.7 minus our 35, which comes out as 64.7 minus 35, comes out as 29.7 centimeters squared. So 3 significant figures. So that's that. That's it done. Okay, that's how we work with these A-level questions. In the lesson and beyond, I'll be giving you support on how to do these questions, and we may well have 2 lessons this week on this topic. We'll just have to see how it goes. But in the meantime, post any questions you have in Teams and work through the questions that I've put in the lesson plans area. All right, thank you very much. Bye-bye.